So, did we go through yesterday's work? It's a question. Did we go through yesterday's work?
Yes.
We did.
Yeah.
On grouped data. Now we can find the mean, the mode, and everything on grouped data.
Yes.
Any question on that? Any questions on grouped data? It's clear. Grace, any questions on grouped data? Okay, so calculations on grouped data are okay for everyone here. Is that what I'm getting? I'm not getting responses.
Yes,
So
we
I
are
want
right.
to know.
We are right.
Okay.
Yes, since there is no one who is coming up with some questions, which means we are fine.
Okay, so let's just go through the assignment 1 again. That will help us get a good revision on grouped data.
Okay.
Okay, so today we begin probability. We'll go up to, from probability, we'll go to probability distributions.
Sorry, madam.
Yes?
Could we kindly have everybody else who has their mics on to turn them off, especially Harrington?
Okay. So let's have our mics off. So let me just switch off some mics. Okay, is it okay? Now I'm not able to hear any noise. Maybe we can proceed. Okay, those that are joining, you're welcome. Okay, I think we can proceed. So we're talking about probability. Now, probability is a very common term. Probability needs your understanding. So the hard topic, you just need to know what is happening. So with probability, we'll first look at ways of finding probability, common rules. We're also going to look at the Bayes theorem, and then this other stuff, we're going to look at it next week. Okay. So probability is just the chance of an event occurring or happening. And probability is between 0 and 1. Okay, so whenever you are finding the probability, it should be between 0 and 1. It should never be 2 or 3 or 10. So even though you may not have gotten the correct answer, but the moment you just give me a 2 or a 3, I should give you a -1 because you're not understanding the concept. Okay, so probability should only be between 0 and 1. Okay, so Is that William? William, what are you doing in this class? Okay, we proceed. So probability should just be between 0 and 1. Okay, and an experiment is just the process of obtaining an uncertain event. Now, there are terms that you need to know, things like an elementary event. So an elementary event is just an event that comes from a simple experiment. Then the sample space is just a collection of all possible elementary processes. Now, there are also terms that you need to know when we're talking about probability, things that we'll be using, like a deck of cards. Does anyone know what a deck of cards is? A deck of cards?
In Joker.
Mm-hmm.
In Joker.
You what?
Joker.
Okay, in Joker. Okay, so those same playing cards that we know. Yeah, so the same playing cards that we know, we'll be using them in probability. So it's good that you know them. How many cards are there in a pack? How many?
52.
52?
Yes.
Okay. Okay, so what colors of cards do we have?
We have two colors. Two colors, red and black.
Red and black, right? So how many aces do we have in the deck of cards? Aces.
We have 4.
There are 4 aces, right?
Yes, ma'am.
Of which 2 will be red and 2 will be black, right? Isn't it? Okay,
that's true.
So yeah, so we need to know the number of cards that are there in the deck of cards, and you also need to understand a die. How many faces does a die have? How many?
2.
6.
Hey.
6.
6.
6, yeah, 6 faces, right? And what options are there? When a die is rolled?
6 options.
There are 2 options. 6. Is it?
Who is
There are
saying 2? Okay,
There are
so
6 options.
6. So a die has 6 faces. There's a 1 where you just find the 1 dot, right? A 2, a 3, a 4, a 5, a 6, you know? Okay, then we need to know a coin. We all know how many faces does a coin have?
2.
For a coin, how many?
2.
2.
2.
So, and that is what? A head or a tail, right? Okay, so what is the probability of obtaining a head when you toss a coin?
It's half.
How did you get the half?
0.5.
Probability. Yes, how
So
did we get the
it's-
0.5?
It's a tail and head. When you add this, it's like no, it's
Yes,
one
no,
of
you're right. We just need The answer
yeah.
is correct. I just need us to understand how we got that answer.
Yeah, so head and tail. There are two events happening here. The head and the tail. So if you pick one of them, it will be out of two.
Okay.
Either a head or a tail. So it will be one out of two, which is half.
Okay. Okay, so yeah, we understand the coins and the options that are there. Okay, I need slide number 3. Okay, so probability. This, I think we've already talked about it.
Mrs. Monday, I can't see the slides. Where do I access them?
Just on your screen.
I can
right
only
now
see
it looks blurred. Pardon? You can only see the...
everyone's faces, yeah. No slide.
Okay.
At the bottom there, there's something showing like a desktop. She can click on that on the bottom right.
Okay.
No, that is for sharing. That is for sharing a screen.
No,
it's not for sharing.
He's right. Thank you.
Not for sharing.
Oh, you mean she should click on that? Okay. So it's sorted now, right? Okay. All right. Okay, so now that is just the die, the options on a die, and a deck of cards. Okay, so an elementary event. Brent, is that your mic? The noise in the background. Okay. Okay, so we have an elementary event and just an event. So an elementary event is just an outcome from a sample space. Like it only has one characteristic, like a red card. Okay, there's nothing else. The probability of obtaining a red card from a deck of cards. Okay, and an event may involve 2 or more outcomes. Like we say, the probability of obtaining an S, which is also red. So in that case, there's a probability of obtaining an S, and also that S card being a red card. So in this case, we have an event, but an elementary event just has one characteristic. Okay.
You can download it.
Okay, so one thing that we're going to use to visualize probability are contiguous tables and tree diagrams. So we talked about contiguous tables, I think, in the first lecture. Yeah. Okay. William, in the background. Okay, so that's what we have. We can use contiguous tables or tree diagrams, and we're going to see from examples how we get that. So how many black cards do we have there in that contiguous tables? How many cards are black?
26.
26. And how many cards are S's?
Yes.
S's.
Yeah.
4.
How many are not S's?
48.
So you really need to understand these tables, okay? So from the same data, we can construct a tree diagram. Okay, so now we have an example. An automobile consultant records fuel type and vehicle type for a sample vehicles, two 2 fuel types, gasoline and diesel, and then 3 vehicles. Okay, so the first started with having those options. So your tree diagram, the branches that you have is determined by the options or the subgroups that exist. In this case, for the fuel type, we just have 2. So that's why we have 2 branches. And for each fuel type, we now have the vehicle type, which has 3 branches because there are 3 types of the vehicles. So what determines the tree diagram is the okay, Chilambwe.
Madam, there are people in the background who are making noise.
Okay, I've just muted their mics. The mic. I've just muted the mic. So then we have different types of events. We have mutually exclusive events. We also have independent events. So we start with the mutually exclusive events. So these are events which cannot occur at the same time. Okay, so they do not have. Okay. Yeah. So these are events that cannot occur at the same time. So, and they do not have an intersection. So whenever there is no intersection between those 2 events, then the events are mutually exclusive. There's a way to find, to know if 2 events are mutually exclusive. That is, if the probability, so we say event A and B are mutually exclusive if the probability of A intersection B is equal to 0. So events A and B are mutually exclusive if the probability of A intersection B is equal to 0. So if the probability is equal to 0 of the intersection of those 2 events, then those 2 events are mutually exclusive. Okay. So that is the test for mutually exclusive events. Now, independent events are events. So examples of, what are some of the examples of mutually exclusive events that you can think of? So being male or female, that event is mutually exclusive. You cannot, the intersection is empty. Okay. And also, there was another example.
The example of a coin, you can only have a tail or the face side.
Mm-hmm. Yes. It can either rain or not rain. You cannot have both. Okay. What other examples are others thinking about? What other mutually exclusive events can you think about? So you can either be married or single. Okay. So those are mutually exclusive events. Okay.
What about divorce and widowed?
Okay, so we can go on. Pardon? Even a program of study. I think programs of study are also mutually exclusive. You can. The mic is, you're kind of breaking.
Muvita, if you're divorced, you're single. If you're widowed, you're single. You're no longer married.
Okay. Yeah. Okay, so even the program of study, you're either you're doing beefing or bachelor's of arts with economics. Okay, you cannot at the same time you cannot be in two programs of study. So those are mutually exclusive events. Okay, so maybe we can think about other. Okay, so dead or alive. This is a good one, I think. Dead or alive, you cannot be both. No. Okay. Okay, others are still typing. As we are still waiting for more examples, we go into independent and dependent events. Now, independent events are events where the occurrence of one does not affect the probability of the other. The occurrence of one event does not affect the probability of another. Okay, so now with independent events, these events can take place at the same time. Okay, but what we are just saying is that when one occurs, the probability of another one occurring is not dependent on the other. It's not affected or influenced by another event. And for dependent events, it is the opposite. The occurrence of one affects the probability of the other. Okay, so we come now to examples. The probability of a person carrying an umbrella may be affected by the weather report or maybe the weather at the moment or of that day. So carrying an umbrella may be affected by the weather of the day. Sometimes if it's too dry, you may decide not to carry an umbrella. Okay, so those events now become dependent, okay, because you are considering one event before taking another, okay. Then maybe again another example would be the kind of program or career that you choose or the program to study may be dependent on your results, okay, grade 12 results. So there, the program of study that one decides may be dependent on the results that one has, okay. But there are other, again, independent events, okay. Showing that I am not connected. Okay, okay. I think I'm connected now. Yeah. Okay. Then for independent events, sometimes you may associate coming late for work with maybe the number of children that one has. Okay. But maybe it would be interesting to carry out a study. Are those events independent or dependent? Whether one has a lot of children or has a child or doesn't have a child. So those are the kind of questions that we want to answer as statisticians. Okay, is that independent or dependent? So I'm bringing it back to us again. What other examples can you give of independent or dependent events that you know or that you might be thinking about? Yes.
One example that I can give is dependent events is where if you do not study for your exams, you will not make it.
Mm-hmm.
So for you to pass your exams, you have to study. So the event being you studying, and the other event being you passing.
Okay. Okay, that's a good one. What are others thinking about? Are we understanding the concept on independent and dependent events? Okay, if there are no more other example, we can move on how to assign the probability. I think earlier when I asked how to obtain the probability of the head, Bessie is asking for an explanation on independent events. Anyone to come in and help and explain independent and dependent events? Okay, when I've explained, I'll just explain once. I'm expecting, and I know that you guys got what I said, at least one. So please, let's feel free and explain to our friend.
Okay, maybe let me try. Independent events are events of which the outcome does not affect the possibility of another event occurring. Like, example, let me just use the one you used for the rain. So might say that you put up the garbage outside, and then you say, whether it rains or it does not rain, still more the garbage will be collected. So those events are independent because they do not affect each other.
Okay, your line was breaking earlier. I think maybe you can just start all over so that we get it clear.
Okay. I was saying independent events, they are events of which the outcome of one possibility does not affect the other. For example, if you look at the weather, whether it will rain or not, and then you put up your garbage outside to be collected, your garbage will be collected whether come rain or come sunshine. So those two events, they are independent because whether the garbage will be picked or whether it will rain, still more the garbage will be picked. Even if it rains, it does not affect the outcome of garbage collection.
Okay, I think that was quite clear. So the occurrence of one does not affect the probability of the other. Okay, so what we're just saying, for the rain raining and garbage being collected, we know clearly that they are independent. But the rain raining and carrying an umbrella, those are dependent on one another. Okay. So now we got to how to assign the probability. I asked a question earlier on how to find the probability of obtaining a head. So we said that there are two options that are there, that is a head or a head and a tail. So the total number of possible outcomes was 2, right? And obtaining a head is just one of the options. So the probability then becomes 1/2. So this is the same probability that is there, the formula. Number of ways of E1, an elementary outcome occurring, over total number of elementary outcomes. Okay, so we can get the relative frequency or empirical probability, which just says number of times that n can occur over all the number of occurrences. Okay, so you will also see how to use this formula. Then probability can also be subjective, an opinion or judgment by a decision maker about the likelihood of an event. So this is subjective, we don't usually use it because it differs from person to person. So we usually use the classical or the empirical probability. So this is the formula that we really know, and this is the formula that is the number of ways that an event can occur over total number of ways that all the events can occur. Okay. Now, with probabilities, we also deal with counting techniques. Do we have our calculators with us? Do we have them?
Yes.
So before we go into probability, it is important for us to understand the counting, the counting rules. One of the counting rules is combinations. Now with combinations, we are just interested in if you have X. Okay, so we're saying we can use the combination formula to determine the number of combinations of n objects taken X at a time. So if we have 10 balloons and we want to pick 2 at a time, how many options do we have? We have 10 balloons and we want to choose 2 at a time. How many options do we have? In how many ways can we do that? Okay, sometimes we are interested. How many? How many times?
5.
5? 5? So you're saying just 5?
Yes.
Okay. Okay, and then there are times maybe you have a committee comprising of 15 people. Okay. Now in this 15, there are 7 male and 8 females. And you want to choose a subcommittee with 2 males and 3 females. How many subcommittees, in how many ways can you do this? So those are the kind of questions that uses combinations and permutations. Now in combinations, we are interested in making a combination, a combination out of making a subgroup out of all the elements, but in combinations, we are not interested in the order. Okay, so if we are choosing 2 letters from 6 letters and we have A, B, C, D, E, and F, and we just want to choose 2 letters, okay, so we can choose AC, we can choose AB, we can choose DF, okay, but even though we can choose CA, so we consider CA to be the same as AC because the order is not taken into consideration. Now, getting back to the combination formula there, it is important for us to know the formula, but this formula is also embedded on our calculators. For us, using Casio, under alpha, there is a button written N capital C R. Can we see that? N capital C R. Can we see that button?
Yes.
So anyone different using a different calculator?
I'm using Sharp. N capital C small r is on the number 5.
So that is the combination function. Okay. So what that n, whatever n that you are having, you press it first, say a 10, then press on that button it will give you a C on the calculator and press a 2. So there you are saying that you have, look at your notes, you have a combination of 10 objects and you're taking out 2 at a time. So this is the NCX. Now on our calculators is NCR. Okay. Pardon? The example that I'm giving is N is 10 and X is 2. Yes. So the answer is 45. So that just means that if we have 10 objects and we're taking 2 at a time, we can do that in 45 ways. So we can use the formula, but this formula is embedded on our calculator, so we just need to know that function on our calculators. Then apart from combinations, there are also permutations. Now permutations takes note of the order. So for example, if we have letters A, yes.
Sorry, I think I'm lagging a little behind. The formula that's embedded in the calculators, NCR, what do we punch in to get the 45? The 10, the 2, what? Because I've punched it. And
so you say 10?
Where the figures go. Maybe
okay, so 10, you go on your NCR function on your calculator, and then you press a 2 and you say equals.
Okay,
so what the function does, NCR function, then 2, then equals.
Okay.
Yes.
It said incomplete expression.
Pardon?
It said incomplete expression.
Okay, what calculator are you using?
It's just a scientific calculator downloaded.
That one is disqualified.
On the number 5, like Roy said. It's got the function NCR on the number 5, like Roy said. So I think it's a download from Sharp.
Yeah, okay. Oh, okay. So on Sharp, what are you doing on Sharp?
On Sharp, you can press 10, then go to second function. Go to second function, then press 5, like 5. Then you press on the number. Let's say, so press 10, second function, then press 5, then press 2 to give you 45.
Okay. And did you get that?
I did.
I think so.
It's just not happening. Okay, I'll find another calculator and try as we go on.
Find your permanent calculator because you need to know your calculator.
Yeah.
Different calculators may have different modes and different functions, so you need to know your calculator.
Okay,
so please find, okay. So that's with the permutation. So I'm going to give you questions that will utilize the combinations and permutations. So the permutations takes order into consideration. For the permutations, when you have an example A, B, C, and D, and you want to choose 2 letters at a time, so you can choose A, B, you can choose A, C, you can choose A, D, right? You can choose B, C, you can choose D, B, okay? Yeah, okay, let me just, okay, so you can choose DB. Now, it takes order into consideration. That means that you can also choose, we had an AB, right? We can also have BA. It takes BA as another term because they have a different order. So permutations take order into consideration. So when you're carrying out the permutations, you find that you actually have a lot of options. The combinations will just take A, B to be the same as B, A, because those are the same letters that you have obtained. So in our example, let's have 10 permutation 2. Now, usually the permutation function is like on a sharp, it is the second function of the combination function. Have we seen that? We have. Those using sharp, where is the permutation function?
It's on top of 6.
On top of 6. Okay. So now let's do 10 permutation 6. Yes?
90.
Okay, so it's 90. That was the question? Okay, I thought that was the question, but I'm not getting it. Okay, so that was on count. Yes?
You said 10 permutation 6 or permutation 2?
2. Okay. We just wanted to redo the previous one now with permutations instead of combinations. So you actually see that the permutation are a lot, that's 90. Okay, so when we choose 2 from 10, the combinations doesn't care about order, but permutations cares about order. Okay, so now we can get back to our rules of probability. As I have said, probability is just between 0 and 1. And sum of all probability is 1. So if an event, say you have the probability of obtaining a head or a tail, and the probability of obtaining a head is 1/2, what would be the probability of obtaining a tail?
1/2.
It will be another half, right? Why are we saying it's another half? And it's because even these two, they should add up to what? 1, right? Now, what if that coin is biased? Like the coins that you find in casinos, they are not normal coins. They are being tampered with. And you find that in that coin, the probability of obtaining a head is a 3/4. Okay. Okay, let me say a 2/5. What will be the probability of obtaining a tail on that same coin that is tampered with? So sometimes in casinos, they tamper with coins so that maybe they want people to be losing so that they have, something like that. Then the probability, they tamper with it in such a way that they make it heavier on the head so that when you toss it, it automatically falls on the head. So such coins, we say they have been tampered with. Now, if the probability of obtaining a head on such coin is 2/5, what is the probability of obtaining a tail?
It's a 3/5.
How did you get that?
Since the total probability is out of 1, so you subtract 2/5 of 1, then that gives us the remainder of getting the other probability, since there are only 2 possible outcomes.
Yeah. Okay, so we use the fact that the sum of all probability should be 1. Okay, so that was also highlighted there. It is also known as the complement rule. So if we are told that the probability that on that particular day it will rain is 7/10, what is the probability that it will not rain? So it is the probability that it will not rain. So not raining is the complement event, a complement of an event. So we say not raining. So if we have the probability of raining, then we can definitely get the probability of not raining. And that is just obtained by 1 minus the probability that it will rain. Okay, is that clear? Okay, so we have some rules for probability. The first one is the additional rule. Probability that event 1 union event 2. So whenever we find a union, this is the same as the probability of E1 or E2. Okay, so we're using or there. Probability of E1 or E2 is just the same as probability of E1 union E2. Okay, so union E2, and this is just given by the probability of event 1 plus the probability of event 2 minus the probability of E1 intersection E2. So that and we also call it intersection. Okay. So it is given there graphically. If we want to add this probability, then we add the individual probability and subtract the intersection because we cannot count the intersection twice. Okay, so there's an example there. Probability of a red or S. Okay. So you can say you can actually, when you are answering these questions, sometimes some events have longer names. So you can say let the event red be defined by R or be denoted by R, and event S be denoted by A. Then you can proceed. Probability of R or A. It's just the probability of R plus the probability of S minus the probability of the intersection. Now, what is the probability of obtaining a red card? The red card is 26, right? Out of 50. Remember, number of ways that an event can occur over all possible outcomes. So it's red cards are 26 over all the cards 52. Then S's, number of ways that that event can occur. S's are 4. You divide by all the cards, which is 52, minus the probability that it is red, the card is red and is an S. Red and an S, which is that 2, right? Over 52. Then you just do the computations and you find that answer. Okay, so I'm going to give an exercise. The probability that it is not an S, not non-S, or red. What is it going to be? The formula? The probability of the card being a non-S or red. Yes. Oh, that's the text. So what is the formula? Or we're working out the whole answer?
Over 52.
$48 over 52.
Come again.
Okay, let's find the final answer. Let's find the final answer. Okay, there's some noise in the background. Have we found the final answer? Have we found the final answer? Yes? So the final answer is a 0.4, 0.46, 0.46. What are others saying? Okay, I have a different answer here. Are we still calculating? I'm waiting for the answers. Yes, we're waiting. Yes, we're waiting for the answers. Okay, there's 0.85, there's 0.46, there's 0.5. Okay. What are others finding? What are we finding? So we are looking for the probability that the card is non-S or red. Okay, so we have 0.519. So we're getting quite different answers for this same answer. 0.96. Okay, 0.5. Okay, let's start with the formula. What will the formula be? Probability that the card is non-S or red. Let's start with the formula. So non-S, let's say that event will be represented by NA and red will be R. So what will the formula be?
Let me try.
Yes.
To be probability of getting a red plus probability of getting a non-S minus probability of a red and the probability of a non-S.
Okay. Okay, so that's okay. Now, what is the probability of obtaining a red card?
It's 26.
26?
26
so
over
that,
52.
Yes.
Over 52.
A 26 should not be the only answer. It should be 26.
26. Yeah, 26 over 52.
Okay. And the probability of obtaining a non-S?
48 over 52.
Okay. And the probability of obtaining both a non-S and a red card? Probability of obtaining both a non-S and a non-S and a red card?
24 over 52.
Okay, so these are the correct numbers that we should have put on our calculators. So Roy, you had a 4 over 52. Where did you get that? And what is that probability? And those that got a 4 over 52.
Well, from the question that you asked, you said, what is the probability of getting a non-ace and the card should be red? Oh, oh my God. Yeah, and the card should be red. Yeah, so, oh no. Okay, bye.
Okay. You've seen where the mistake was?
Yes, I do.
Okay, so we should be very careful with such questions because they may seem to be simple, but you just need to be careful. Okay, so our answer is 0.96. Yeah. So we just had this question and we had 5 options. So I don't know what others were doing, but this is what we should have done. Okay. So now we also have the addition rule for mutually exclusive events. So what did I say would be the intersection for mutually exclusive events? For any 2 events? The intersection for mutually exclusive events?
Intersection
what does it become?
Is the 0 since they can't occur at the same time.
Yes, so the intersection is 0. So remember, in our formula, what did we say? We said the probability of E1 or E2 is just the probability of E1 plus probability of E2 minus the probability of the intersection. Now, in this case, the intersection is 0. So that means the probability of E1 or E2 is just the adding the individual probabilities because there is no intersection. So when you find a question, begin using this formula, like use the formula, the normal formula. Don't just say probability of E1 or E2 is E1 plus E2, probability of E2, because you may not know whether they're mutually exclusive or not unless you are told. Okay. Okay, so now we go to conditional probability.
Sorry,
Okay,
sorry,
so
madam.
Yes, sir.
Could you kindly go back to the previous slide?
Okay. Yes.
So, madam, in this case, the and will always mean it's an intersection.
Yes.
Oh, okay.
So E1 and E2 is just the same as E1 intersection E2. Then the O here is the same as the union. E1 union E2. Remember, even in the previous slides, we say in the formula for addition, we can say E1 union E2. It's the same as E1 or E2. So O can be used for union and can be used for intersection. Okay, so now we go to one of the interesting subtopics on the conditional probability. So we're saying that we can have some conditional probability. So we read the probability of E1 given E2 is just equal to the probability of E1 intersection E2 divided by the probability of E2. So here, note that the probability of E1, the conditional probability of E1 given E2 is just given by the numerator, which is the intersection over the condition, the probability of the condition. And the condition in this case is event 2, which is E1, E2, I mean. So this is the formula. You will just have to remember. So if we had probability of A given B, we'll say this is the probability of A intersection B over probability of B. So we divide by the probability of the condition. Okay, so we're given an example of the cars on a used car lot. 70% have air conditioning, which is the AC, and 40% have a CD player. 20%, okay, so 70% have got AC. What is that probability? The probability of AC
is 0.7.
0.7, right? And the probability, no. Okay, so the probability of CD, of a CD player,
0.2.
probability, no, probability of a CD player. You're told 40% have a CD player. What is the probability of having a CD player? So 0.4, okay? And the probability of having both, that is AC intersection CD, is 0. Yeah, it's 0.2. Now we are looking for the probability that that car has a CD given that it has an AC. It has a CD player given that it has an AC. What is the formula going to be?
It's going to be probability.
I'm waiting for the formula.
Can I try?
Yes.
It's going to be the probability of CD given AC is going to be equal to the probability.
CD.
Oh my God.
It's going to be equal to?
It's going to be equal to the probability of CD intersection AC over the probability of AC.
Okay. And we can go ahead and compute what is the probability of CD intersection AC. We already have it at 0.2, right? And the probability of AC, 0.7. 7. And what do we get?
3.4 plus 5. 0.7.
What are we getting?
0.28. 0.285.
Okay. 286. Because that 5 after 5, there's another big number.
Then it's 2/7.
Okay, 2/7 is still the correct answer. Okay, 2/7 is still correct. It's just in fraction form, but it's a correct answer and acceptable. Okay, so that question was given in form, can be given in form of a contingent table. Okay, so from that, let's have the probability of no AC given CD. Let's find that probability. Probability of no AC given CD. Probability of no AC given CD. So I've asked the probability of no AC given CD. Anyone to give us the formula?
Should be
Okay, so what's the answer? What's the answer? No AC given CD. I don't see the answer as being typed, or you can even just tell us. No AC given CD.
Madam, I'm finding 0.75.
0.1? 7?
75.
How did you find that 0.7? Because it's wrong.
I'm finding 0.3.
0.3 is also wrong. A 0.5 is correct. 1.3, 1 over 3 is wrong. So you guys, we have not even moved anywhere and we're finding various answers. Yeah, 1.2 is correct. 1 over 2, I mean. So what is the formula that we're going to use? No AC given CD. The formula?
Formula will be intersection AC. Probability of CD.
Over probability of CD, right? And what is the probability of no AC intersection CD?
0.1. 0.1.
No, 0.1 is no CD intersection, no AC. You see, that is the 0.1. Now you're looking for no AC intersection CD. Where no AC meets with CD, it's at 0.2. Now we're together. No AC intersection CD, that's a 0.2. And what is the probability of no over CD? Of having a CD?
0.4.
0.4, so that is our denominator. So it will be 0.2 over 0.4, which gives us a 0.5. Is that clear? Okay, then let's have AC, probability of AC given no CD. Let's compute that. Probability of AC given no CD. Okay, so we should be winding up because we have taken over an hour.
0.4.
Okay, let me just find it as well. We said AC no CD. Okay. No CD. What are others finding? So what did you say?
0.4.
No, 0.4 is wrong. Pardon? What are we finding? So 0.7, 0.8.
Madam, I'm getting 0.8 on this one.
Okay, 0.8. 0.8 what?
0.8.3. Sorry, 0.83.
Yeah, that's okay. That's correct.
Because what I did is, given AC, it's 0.5 divided by the total, which is 0.6. It will give us 0.83.
Yes. Okay. So then let's find the probability of no AC given there's no CD. No AC given no CD. Let's find that probability. No AC given no CD. given no CD.
Let me just give it a try, madam.
Yes.
0.17.
We want to know how you got it.
Okay, you're saying no AC given no CD.
Yes.
We go to no AC where it's meeting no CD. That is 0.1 over the total 0.6.
Which total is that?
The no CD one.
Okay. Yeah, so 0.17. Yeah, 167 or 17 is still okay. Okay, so for independent events, we move on. We have a formula for testing. So we're saying probability of E1 given E2 is the same as the probability of E1 if those events are independent. So what we're saying is that we have a conditional probability there. E1 given E2. Okay, but if this E2 has no effect, if the E2 has no effect,
0.4.
Okay, what is the 0.4?
0.4.
What is the 0.4? Okay, so we continue with the test for independence. So probability of E1 given E2 is the same as, is just equal to the probability of E1. So I gave you, say that probability, I think it's also in the assignment. I asked you on that. So if probability of A is 0. I'm giving an example, 0.2, and the probability of B is 0.4, then the probability of A intersection B is 0.1. Are events A and B independent? So what you do there, probability of A is 0.2, probability of B is 0.4, probability of A intersection B is 0.1. Are A and B independent? The formula there tells us that A and B are independent if probability of A given B is the same as probability of A. Okay, so what is this probability of A given B? We know it's the probability of the intersection over the probability of what? B. Isn't it? Are we together?
Yes.
The probability of intersection is 0.1. The probability of B is 0.4. So when we do that, we're going to say 0.1 divided by 0.4. It gives us 0.25. Now, we're saying that for independent events, the probability of A given B should just be the same as the probability of A. So for conditional probability, we found 0.25, and the probability of A is just 0.2. So since these two are not equal, it means that they are not independent. Okay. Are we together? Clear? Okay, sorry about that. So that is the test for independence. If these are not equal, then they're not independent. Okay. Okay, so I think we'll end on conditional probability, seeing that there's no, I think we've gone up to 30 minutes. So on Monday, we're going to finish up on the multiplication rule, and I will start the Bayes theorem. So just read on this, and yeah. So any questions on what we have done today? No questions? Is it clear? Now we are becoming experts in probability.
Yes.
Okay, so there's a test. I said on Friday, today, there's a test that is open on Moodle. I think it should be quiz A or quiz 1. I think it's quiz A. So you can take that quiz as many times as you can. It's a practice quiz on introduction to statistics, measure of central tendency, and probability. So please try those questions over the weekend, as well as the assignment 1, especially question 1 and 2. So far from what we have done, I think 1, 2, 3, we should be able to answer those questions. So let's redo the assignment for the sake of practicing. Otherwise, I think we'll end here. Okay, thank you.
Okay, thank you, madam.
Okay. Okay, someone still typing something? Okay.